Okay, so why don't we get started? And this session, we'll talk about carbon removal. And this has been, the last few years, this has been a very hot topic. And probably most of you have read something about it because it's been almost every day there's news articles somewhere on this topic. In fact, there was a 60-minute segment on this about 2 months ago on national TV. So why are we interested in negative emissions? And this is a graph from one of the IPCC reports showing carbon emissions with this area here, this light gray. What that is our emissions, and then these in the brown and the yellow are negative emissions. And, you know, for us, well, go here. So they look at two types of negative emissions in this scenario. This is basically to do with land use, forestry, afforestation, forestation, and land use changes. So this is putting CO2 into the terrestrial biosphere. This is using bioenergy and CCS. You get a similar thing if you're using direct air capture. And we'll go through the different ways to do it. But generically, just to show what it is, when we reach this point, we're at net zero. That means our emissions are counteracted by our removals. And once we move beyond there, once we move beyond there, when we're down here, we're actually net negative, where we're taking more carbon out of the atmosphere than we're putting in. And in a minute, I'll talk about why people are interested in net negative. So, as I said, this has become a hot topic recently, but a lot of the people have been looking at this for, well, quite a while. I know some of the first papers on direct air capture came out right around the year 2000. These are some major reports from the government. This first one's from the National Research Council, looking at carbon dioxide removal. The second one, where's that from? Once again, it's from the National Academies. It's a different part of the National Academies, looking at negative emissions. So sometimes these carbon removals, they call them negative emissions. And so once again, why are we looking at it? So there's two major reasons. The first here is offset, and that helps us getting to the net zero that we showed. So I go back here. This is right here at net zero, where we're offsetting remaining emissions with negative emissions. And to do that, we'll probably need gigatons per year. And if we look at, so that's the scale, how many gigatons is up for debate. People, if you go in the literature, you can see numbers anywhere from 2 gigatons a year to 20 gigatons a year. Remember, we're putting out about 40 gigatons per year. But the idea here is that the cost of the negative emissions will be less than the marginal cost of mitigation. And so if taking CO2 emissions off of the airplane to decarbonize an airplane may cost you, say, $800 a ton of CO2, if I could do negative emissions for $400 a ton of CO2, I'm much better off offsetting it than trying to re-engineer the airplane. What are these difficult emissions? This is just one example from one article. It's showing total emissions at 34 gigatons, and they're saying we have to do about 9 gigatons. So that's a little less than a third, 30%, or just under 30%. And they come from areas what they call load-following electricity. So while renewables are good, they're intermittent, and we need something to help balance the load. Something to help balance the load, and that's what this is from. We talked about iron and steel and cement being hard to decarbonize, long-range shipping, long-distance road transport, aviation. So those are some of the areas. This is just one example of doing it. You look in the literature, you can get many different examples, but this is saying, well, we may need 9 gigatons of offsets to reach net zero. And in addition to these, there's other things. These are just from energy. There's other sectors, as we talked about, agriculture, especially ammonia fertilizers producing N2O out there. So I think there's going to be a need, and this is why the interest in this subject. But people are also interested in this subject because of net negative. And basically, as I said, the aspirational goal is to be 1.5 degrees C temperature rise, but definitely under 2 degrees C. Unfortunately, we're decarbonizing very slowly, and it's becoming fairly clear we're going to overshoot those things, so that's called overshoot. But if we overshoot and then we go net negative, we can come back and hit those temperature targets. So we can actually start cooling the Earth by going net negative. It's probably going to take a lot more negative emission to do that. Instead of on the order of scale of gigatons, probably need tens of gigatons. And here's the real thing. The cost is going to be much greater than today's mitigation cost. So today we can mitigate a lot for under $100 a ton. But if we want to take that out of the atmosphere later, it's going to cost hundreds of dollars a ton. And so, that's sort of a moral dilemma. And that's why some people get upset at talking about negative emissions, because what we're doing is saying we're not going to pay the low money today, but we're going to have future generations pay a lot more money to clean up the mess we leave behind. So that's why people sometimes say that use the term. I'm trying to think of the exact word. More, it's sort of a moral dilemma going there, and they don't think we should do that. So, in summary, so it's going to be very hard or probably impossible to reach net zero without these negative emissions. But whether we're going to need to go net negative in the future, I actually think that is a distraction today when we're talking about it. And why is that? Because it's going to take us decades to get to net zero, and you can't get to net negative without going to net zero first. And in several decades in the future, we're going to have much more information on the cost of these carbon dioxide removal technologies. We're going to understand better their performance, and we're going to understand their benefits more. So we have that information. So I think that debate should happen in the future and not today. I think there's enough incentive today that we need negative emissions to get us to a net zero world. So what are these negative emission pathways? People divide them up in many, many different ways. I try to keep it fairly simple. Realize there's two major pathways. We can do biological or chemical, and sometimes people say chemical or geochemical. And the biological one is to take CO2 emissions and put them into the terrestrial biosphere, which means our vegetation, our soils, our trees, and quite a few ways to do that. I just have a few examples here. Afforestation and reforestation are a big area. Places that have been deforested, we can reforest them and increase the stock of carbon in those in that land. We can modify agricultural practices, things like no-till agriculture, where when you till the soil, you release carbon, but if you do no-till agriculture, the carbon can build up into the soil. Next one, biochar. Yeah, some people talk about biochar. Basically, biochar is made from trees as a soil additive. It's actually been used a long time, but you can put that in the soil and build up the carbon in the soil, and actually it can help produce, increase agricultural productivity. We can use the ocean, and the major way here in biological is to fertilize the ocean. This is something that was talked about in the 1990s. It was called the iron hypothesis. This guy, Martin, hypothesized that if you put iron in the ocean, you'll have blooms, and it will pull, and the vegetation will put CO2 into the ocean. And actually, they did experiments, and it's absolutely right. There's parts of the ocean which is lacking in nutrients, and has nutrients, but doesn't have iron. And if they put iron in there, they see the blooms. The problem is we're not sure if those blooms lead to permanent storage of the CO2 in the ocean, and even worse, you really change the ocean ecology by doing this. And I think this is not a viable pathway. I put it up here because people talk about it a lot, but I think for the ocean ecology, this would be a very bad pathway to go. And finally, you can put in deep geological formations, and this is bioenergy with CO2 capture and storage. So the trees take the CO2 out of the air. Then when we can convert the trees into energy and capture the CO2 while we do that, we have negative emissions in the long run. There's some issues with this, which I'll talk about, but this is one that's been really, this is probably one of the first that's been talked about as being able to do it on a very large scale. Chemically, there's something called ocean liming, and this is a little different than fertilization. Here you're using inorganic. You're putting basically lime in the ocean or some alkaline material. It could be a silicate rock like olivine, but these are alkaline rocks, or it can be something like calcium oxide, which is lime, and I'll talk about that a little more. I think, well, this is, what should I say? I think this actually has some interesting possibilities. A lot of people are very nervous about this, but I'll talk a little about that later in the discussion. Rock weathering, once again, as I said, this is the way nature does it. Can we accelerate it? People talk, and once again, you need alkaline rocks, so it's somewhat similar to this, except doing this on land. I think this is difficult, but people have some offshoots of this, especially with the cement industry. I don't have time to go into that in the lecture here. I think there's some opportunities, but I don't think it's as big as some people look at it. And then, of course, we have direct air capture, where we use the same type of machines we capture, or similar type machines that we capture from a smokestack to capture from air. So I'll focus on these two, and then I'll talk a little bit about the ocean liming at the end. So, as I said, we have many options, and all of these options have challenges. I'm actually trying to write a book on this, similar to the carbon capture book I wrote called Carbon Removal, so I've been really digging into this, and none of these are easy, and they all have barriers. Some are cost. When we talk about direct air capture, I think that's a major thing there. The permanence is an issue, especially with a lot of the biologicals. The biological things, a lot of times, are called natural climate solutions. You know, so we can put the carbon in the trees and the soils, but will it stay there for a millennia, which we really wanted to do, or even a century? People are looking at sort of a century minimum, but how do you guarantee it that will stay there a century? You know, forests get burnt as we see the air here today, so permanence becomes an issue. So, I mean, it can be addressed, but it's not easy. Additionality, and once again, and I'll show some examples in a minute on natural climate solutions. You know, are you really paying for something that would not have been done otherwise? And you know, if something's being reforested, would you do it anyways, or you want to get paid for it? Monitoring, reporting, and verification is very important. How do you do the accounting? You really have to do a life cycle accounting. If you're going to use energy to take things out of the air and create CO2 by using that energy, you've got to subtract it off. You've got to use the net removed, not the total removed. Are there environmental impacts with what you're doing? I mentioned ocean fertilization. I think this is a showstopper for that. Environmental justice is becoming more and more important in the bills passed by Congress on some of the things that they want to do in the energy. They actually have clauses to show that about environmental justice, that you're not disturbing, you know, that you're helping out the local communities and not causing harm. As I say, there's, in some areas, there's been a growing backlash against some of these technologies. A lot of it is the biological ones, because they're sort of one on the front there. This is, I think, a commentary from The Guardian, just to give you sort of a sample of what people are saying. They say, you know, they talk about unrealistic over-reliance on carbon removal to preserve the status quo. And as I say, if you're going to use carbon removal to preserve the status quo, that's not the way to think about it. The number one thing is to reduce emissions as quickly as possible. But at least certain companies are using this to offset emissions and not doing enough to reduce their emissions today. And the other thing is, you're not, you know, are you really getting what you're paying for in the carbon markets? So there are carbon markets out there today. Some are compliance markets, but most are what's called voluntary markets. So California has carbon regulations, and they have a compliance market with rules that you have to do to meet it. That's a little more strict than these voluntary markets. These voluntary markets, pretty much anybody, any one of you can go set up a carbon exchange and bring together buyers and sellers. Who are the buyers? A lot of companies, the high-tech companies, have been buyers into these carbon markets. Airline industries have been buyers into this carbon markets. And they just want to say, well, we're reducing our carbon footprint by buying this, and the sellers could be farmers, you know, could be forest managers, there could be a lot of things. And all three of the people involved, the broker, the seller, and the buyer, all want to maximize the amount of carbon credits being generated and sold. And so the question is, are those carbon credits real? And then what you get are things like this. This is an example. Nonprofit promised to preserve wildlife, and then it made millions claiming it won't cut down trees. This is the Massachusetts Audubon Society. They have their land. There's no way they were going to cut down trees on their land. Yet actually this is through the California compliance market. They actually sold credits into that market and got paid, I think they got paid $600,000 not to cut down trees they weren't going to cut down anyways. Here you see, once again, this is from the California compliance market. Up to 39 million carbon credits aren't achieving real carbon savings. And you can go through and see lots of articles that said this. There was an article in The Guardian about one of the voluntary carbon markets, Vera, and they said that 93% of the carbon credits were really worthless. And so this gives the negative emissions sort of a bad approach or sort of a bad reputation. So actually then that starts putting more pressure on things like BECCS or direct air capture. We can actually count the carbon you're putting into the ground. There's still other issues like looking at the life cycle, but that's why I think there starts getting more and more interest in this. So let's take a look at BECCS. So capture, there's different ways you can use the biomass. I'm going to talk about BECCS as burning it in a power plant. There are other ways you can move the biomass. As I say, you can make, you can take it and you can make it into fuels and capture the carbon while you do that. And there's other other things people look at the biomass. But I think BECCS is probably the most interesting. And when we look at it, when we look at biomass power plants, there's two differences between biomass power plants and, say, a coal-fired power plant. One, it has lower conversion efficiencies. Why is that? The biomass has lots of moisture in it. Secondly, the biomass actually costs more than coal. So that makes your electricity more than biomass. But what really drives the process here is the carbon in the biomass is worth more than the energy. And actually the modeling, some of the modeling we've done suggests that 90% of the advantage of using biomass in carbon capture, 90% of the economics is going to be driven by the carbon that you're storing, and only about 10% of the income is going to be coming from the electricity. So I think that's an important thing to understand, because as we say, we don't really use biomass as a fuel today to make electricity because it's expensive. So it's really the carbon in the biomass that drives it. The big issue here is how big is our biomass supply chain, and also how sustainable it is. So there's sort of a segment of the environmental community that's anti-biomass. And why is that? Well, they say if you cut down a tree today, let me back up. So like in the UK, they had it that if you burn biomass at a power plant, it was considered carbon neutral. But what the people that don't like it say, well, I'm cutting down that tree today, and even though the CO2 came out of the air, I'm going to burn it at the power plant, all that CO2 is going back in the air today. And then it's going to take decades for the forest to reabsorb the CO2. And numbers that go up to 70 or even 100 years to reabsorb that CO2. So I'm going to have excess CO2 in the atmosphere for maybe up to a century from that. So you can't really look at it as carbon neutral. But if we take that biomass and capture the CO2, then we eliminate that problem. There's still a problem of, okay, I'm not emitting the biomass today, but I cut down that tree, and the biomass I'm going to take out of the air, it may take decades to a century for that to come in. So that may be complicated in how you do the accounting and the payments for it. But at least in terms of climate, we're not making things worse in the short run. When we put something like BECCS or direct air capture in these climate models, this is what happens. So this is from a paper we did, and what these blue lines, well, these lines here, the blue lines the blue lines are without having BECCS available, 2 degrees C or 1.5 degrees C, what the carbon price would be to meet that goal. So of course it's more expensive to meet the more stringent 1.5 degrees C versus the 2 degrees C. But when we have BECCS available, instead of the carbon price going way up like this, it tapers off here. And this behavior they call a backstop technology. Is when you have a technology that gives you, at a certain carbon price, it gives you pretty much infinite mitigation potential. And what's it just saying here, this is being driven by all those hard to decarbonize activities in the economy. But once we get to a point where, in this case, $240, if it costs more than $240 to abate these emissions, we're better off offsetting them and going along like this. So that's what we're doing. Actually, in our model, we had about 20 gigatons of bioenergy in CCS, which I think is a little too much to go there. But once again, this is the type of activity you can do. And this, of course, saves the economy lots and lots of money in getting to net zero. And that's one reason there's all this interest. So let me stop there for a moment before I move into direct air capture. Right? We're going to go into a little more detail. Any questions up to this point? Okay. All right. So let's look at direct air capture. And this, literally, in the last few years, there's been billions of dollars being put into this industry. There's probably, I don't know the exact count. I saw a list a few months ago of over 20 companies doing direct air capture or proposing to do it, and I'm sure that list has probably expanded to over 30 companies today. What is it? Well, what do we do? So we're talking about doing it out of the air, and there's no question we can do it because it's being done commercially today, and I'll show you where that is. It's by Climeworks. Actually, 2 weeks ago, I was actually in Switzerland at the Direct Air Capture Summit that Climeworks put on and gave a keynote talk there. And they were, it was quite well attended. They had like 400 people in person and more than 2,000 people online looking in. I said lots of money, lots of companies, and the real question is cost. So what does it cost? We know a price. That's not a cost. We know you can buy negative emissions from Climeworks today. And how do we know that? Because you go to their website and you'll see this. And so you can do the arithmetic. The arithmetic always comes out the same to $1,200 per ton of CO2, so 96 for 80 kilograms. You just scale that up to a ton, and you get the $1,200. Actually, what Climeworks has told me, their cost for this initial plant is closer to $2,000 a ton per CO2. So this is very, very large. When we're looking at mitigation costs today, we're looking at $100 or less. So this is an order of magnitude more. Question is, can you get it down? First of a kind plants always cost more. When you start replicating, people use solar panels as an example of how expensive they were 20 years ago and how their price came down. Can we do it for direct air capture? I'll try to address that. But how does it work? And it's fairly simple when you strip out all the little details. You basically have absorption, desorption. I think just about every one of these proposed processes do it this way. Here's your absorber. You have air come in and depleted air go out. This happens at low temperature and it's exothermic. But once again, the heat that you get off is really not recoverable because you're doing it at ambient conditions, whatever temperature the air is. Then you have the CO2 rich sorbent. Heat it up at a high temperature. You desorb to get the CO2 off and then bring it back down. There's some potential for heat recovery. Certain processes are better than others. But this is basically what you have. It's not really any different than what we see doing it from a smokestack of a power plant. Let's take a look at the absorber, because there are very significant differences than what happens at a power plant. So there's two types of processes out there, and I'm going to start with what I call the weak base process. So this is mainly using amines, which is a weak base. As I said, amines for the power plant was good. It's Goldilocks. It can grab the CO2, but it's easy to release. Well, when the CO2 is so dilute in the air, it's not as easy to grab it, but it still works. But the amines are not, in a power plant, the amines are in aqueous solution. Here, the amines are basically impregnated on some sort of solid substrate. So you really have an adsorption process, not an absorption process with a D, because the amines are on the surface of your substrate. But once again, you have a temperature vacuum swing. Once again, we raise the temperature to about 100, just like at a power plant. But now, instead of using stripping steam to create the lower pressure, we're actually going to use a vacuum pump. And there's two companies that do this, but Climeworks is really the key company that's out there. And they're the only real company that's doing this at any scale. And even at the scale they're doing it at, their big plant in Iceland is 4,000 tons a year. They are building a 30,000 ton per year plant up in Iceland now. This is actually the plant in Switzerland. I actually looked at it last week. This is actually not running anymore. They do have another plant right next to it that is running. You can see the Alps in the background there. There's some, they don't show it here, there's greenhouses in the field. One of the uses of the CO2, there's two uses of the CO2 that they're doing at this facility. One is they're putting into greenhouses to lift the CO2 atmosphere there to basically fertilize the plants. And the other thing they're doing is they're actually selling some of it to the Coca-Cola company, and they're making some Coca-Cola with basically non-fossil carbon. So this is what it looks like. You can see the way it works. There's a fan. This is actually the exhaust fan, so the air is coming from the other side into here. They let it run a few hours and let the filter pack, the amines get saturated, then they close it, and they basically have metal plates that come in and seal it. They'll pull the vacuum and they heat it up. The first thing they do is they'll pull a vacuum. They pull it down to about 0.2 atmospheres, get a lot of the air out of there, and then what they do is they then heat it up, and that starts driving the CO2 off, and they'll vacuum pump it. They actually have to do a little extra purification because they do have at the 0.2 atmospheres, they get about 5% air in with the CO2, so it's about 95% pure CO2 coming off of here. And so they'll do a little cryogenic distillation and liquefaction of the CO2, and then either send it over to the greenhouse or ship it to Coca-Cola. So that's how this works. Then there's a strong base process, and I'm not going to go into all the details of that, but it's more complicated. They actually do use a liquid sorbent with hydroxides, and hydroxides have a very strong attachment, so it's easy to grab the CO2 out of the air, but they're not easy to regenerate. They call it a temperature swing, I call it a chemical swing. It has to go up to 900 degrees C. They have to do it in a kiln. This is where I talked about yesterday. They actually use an oxy-fired kiln to do this. It's a fluidized bed. My sources tell me they have a lot of trouble doing it. This process, invented by Carbon Engineering, they have a pilot plant out in British Columbia. I visited there a few years ago, but Occidental Petroleum, or Oxy, has taken this. They just had a groundbreaking. They say they're going to do 500,000 tons a year starting in 2025 in West Texas. And my assessment of it is that they have a lot of problems to solve, and they're never going to make that deadline, and I have some real doubts whether this version will be happening. Not only has Oxy said they're going to have it going in by 2026, they also said they're going to have 135 of these within the next decade or so. Yet, they haven't even worked out the problems at the pilot plant at 5 tons a day. So we'll see what happens. This is part of the problem in this field. When there's a lot of money flowing in, people say a lot of things, and we have to just see what really happens. But Climeworks is very real. So what are the differences between flue gas capture and DAC? We've alluded to it, but the big difference here is the concentration, factor of 300 versus a coal gas flue, factor of 100 versus a natural gas flue. And this gives us some real fundamental issues direct air capture has to face. It has to process large amounts of air. So if you dilute it 300 times, you have to get the same amount of CO2 you get out of a coal gas flue, you have to process 300 times as much air. That's a lot of air, and we'll see exactly how much air in a second. It's also going to take significant energy to do that. And we'll look at both of those. So let's look at the air processing. So the air contactor, you have a cross-sectional area and a depth, fresh air in, depleted air out. There's only so fast you can put the air in. Typically, maybe 3 meters per second, but a range of, say, 1 to 5 meters per second is what you can do here. So because of that, you need large cross-sectional areas. And on the next slide or two, I'll show you exactly how large a cross-sectional area. But since there's not a lot of CO2 in the air, it's a fairly shallow depth in the absorbers. So the aspect ratio is very different than we see at a power plant. And here's an example. So this, I showed you Petronova yesterday, 1.6 million tons a year. This is the absorber. You can see the height, and you can see the diameter. So for the flue gas, the height, and to get it on the same, basically the square root of the cross-sectional area, basically the diameter there, you can see that the height is greater than the diameter. I don't know how many times, maybe 10 times or what have you there. Climeworks, and this is only 900 tons of CO2 a year. Your cross-sectional area is much greater than the depth. So even here, basically this is your cross-sectional area, the whole thing here, and your depth is only a couple meters deep. And when you scale this up to do this to get to 1.6 million tons, forgot the number off the top of my head, 1,800 times as much, I think. So you have 1,800 of these. The depth is still the same, but the cross-sectional area is 1,800 times this cross-sectional area. So the cross-sectional area is much greater than the depth. And you can do this exactly. So if you assume how much CO2 is in the air, this is done for 410 ppm. For different capture fractions, how much of the CO2 in the air am I taking out? What's the cross-sectional area you need? So for the carbon engineering design, it came out, I think this is 46,000 square meters. And what's 46,000 square meters look like? It's like a 3-story building, about 3 miles long. Now that's only for 1 million tons per year. So this is a fairly giant structure. Of course, they have to separate it out. You're not going to have one single building, so you have multiple absorbers. I think they're having maybe 30 absorbers to do 1 million tons per year. So said that So you need to figure out how you space these, just like you have a wind farm. You don't want to put one windmill in the wind shadow of another. You don't want to put one absorber in the exhaust of another absorber. You want to have fresh air coming in to minimize their interactions. How much land you need. This is a range that what you see in the literature. Probably for the 1 million tons per year from carbon engineering is probably on the order of 1 square kilometer, fairly big area. And then what you have to do is you have these absorbers spread over that square kilometer, and then you need a central processing station. In the carbon engineering design, you actually have to move solids from the absorbers into the calciner in the middle. But you have all these inputs. All of this basically says it's going to cost you a lot of money. And how much, we don't know exactly, but it's not going to be cheap. And it's going to be a lot. I'll come back to what the literature says and what I think reality is. Energy, that's another big issue here. So looking at the literature, it's about 1,200 kilowatt hours per ton of CO2. Actually, I think that's optimistic. I think today the numbers are bigger. If you look at something like Climeworks, they use both heat and electricity. And if you look in the literature here, and I find the literature on direct air capture very weak. A lot of times what I see them doing is say, okay, I need 500 kilowatts of electricity, 1,500 kilowatts of thermal, so I need 2,000 kilowatt hours per ton of CO2. You cannot add thermal energy and electric energy together. You have to do some sort of conversion. What I've done here for the Climeworks is I used a heat pump. So a heat pump, basically you put electricity in and pump heat. So if it has a coefficient of performance of 3, every kilowatt hour of heat you put in, you get 3 kilowatt hours of, every kilowatt hour electricity you put in, you get 3 kilowatt hours of heat. So if you take, in that case, if you assume a coefficient of performance of 3, you can say, okay, I'll take the kilowatt hours of electricity and 1/3 of the kilowatt hours of thermal, and then I'll come down to this number here that combines the two. So this is on a power basis or electricity basis that does include compression of the CO2 also. So if you're doing this, you have to supply that, and that energy better be carbon-free. If you try to supply it from a coal-fired power plant, every kilogram of CO2 that you capture from the air, you're going to put out 1.2 tons of CO2 from the power plant. So you're actually going to just, you're not doing any negative emissions, you're actually doing positive emissions. Natural gas plant's better, but it's still, you're going to put out about 1/2 ton of CO2 for every ton you capture. And if you do that, that basically doubles the cost. So if you look at the price for ton of CO2, gross ton of CO2 removed is X. If you use a natural gas to power it, then the real cost for net removed is 2X. So you've got to be careful, and you may say, well, that's kind of obvious. When we go to the next lecture on the policy and we look at the 45Q tax credits, they look at gross amount, not net amount for what they're paying you. So once again, we'll talk about that a little more. So let's take a look. If we do this at a gigaton scale, how much energy that would really mean. This is 2019, I believe, 2019 electricity production in the US. Here's how our sources are. And if we're going to do a gigaton of direct air capture, which is about 20% of our total emissions, this is the line we're going to use. And if we're going to use carbon-free energy, which are just three columns, you're going to use about 80% of the carbon-free energy the country's producing today just to do a gigaton. So this is a real issue on the amount of energy you need. You can maybe lower this line, but not by too much to do that. But there's an additionality issue here. I said additionality was one of the issues. If we have this carbon-free energy, is the best thing to do, is it air capture, or is it to sort of drive out other emissions? What else can we do with our carbon-free energy? Well, we can replace our coal and gas in the electricity sector. We can replace retirements of nuclear power plants when they close. We can charge our electric vehicles. We can power our heat pumps. We can produce green hydrogen in addition to powering direct air capture. So direct air capture may have promise 20, 30 years in the future, but today I just think it's not ready for prime time. I think it's good that we're doing research and trying to understand the cost and the best technology, but all this money going into it, I think, is a little misplaced right now in terms of the best strategy to deal with climate change. So let's talk cost. So as I said, it's technically feasible. The real question is cost. So if you look, once again, if you look at the literature, there's a lot of things people say to promote direct air capture. One thing they say is it uses air as a feed stream, so the plants can be sited anywhere. That's true that air is everywhere, but siting's a complicated issue. There's lots of things you have to worry about. Land availability, access to low-carbon energy, access to water, permitting issues, acceptable meteorological conditions, accessibility of storage options, among other things. I should say something about meteorological conditions. I mean, first of all, these units have to be hardened to wherever they are in the environment. Climeworks has a unit up in Iceland. They've learned to harden it, but the first winter they were up there was a lot of downtime because it wasn't hardened at that point. Hardening's not necessarily a very complicated issue, but once again, it's a cost issue of doing it. And meteorological conditions also affect it. So in Climeworks, not only does it absorb some CO2, it also absorbs water. And even though the water doesn't take the sites on the sorbent away from the CO2, when you vacuum pump, you have to vacuum pump the water along with the CO2, and that costs money. So you'd like to have sort of drier conditions. The carbon engineering that I said there's an aqueous solution, they're in a different problem. If they want to be, they like moisture. If they're in a very dry area, they'll have a lot of evaporation because you have a lot of air going through. It's going to evaporate a lot of that water, and so their water usage will go up, and that will cause an issue. So once again, meteorological conditions, the moisture is one thing, temperature is another. The carbon engineering, because it's an aqueous solution, really won't work when you're really down. Basically, they told me below 40 degrees Fahrenheit, you run into problems. Cost myth 2, there's unlimited feedstock of air, so you can choose any capture fraction you want. The statement is true, but it's totally irrelevant. The reason for that is the amount of air you want to capture out of the airstream coming in is really a function of your design. It's really a trade-off of capital and energy and some other things in your design, and so therefore it's a dependent variable of the design process, not an independent variable. And usually that number is in the 60 to 75% range when you look at it. Actually, Climeworks, when they have a fresh filter, though they may do 75%, but by the time the filter is getting saturated, they may be down to about 60%. 3, people talk about waste heat to do the regeneration energy. You're going up to 100 degrees C. Question is 100 degrees C really waste heat? But there are opportunities where there is excess heat in the process. But if we're going to go to a gigaton scale, that's going to be just a small fraction of the installation. So there's not that much waste heat around. So people use this to get optimistic about cost. So where are we? Many papers say we can do this for the $100 to $300 ton range. The Department of Energy put a target of $100 per ton CO2. And these estimates are not just credible. As I said, Climeworks, when I was there, told me $2,000 a ton of CO2. They hope by 2030 to be in the $400 to $700 range. In the paper I wrote, I said it'd be more in the $600 to $1,000 range. That's on the optimistic side, but I think it's possible by 2030 that we can hit that target. So I'm going to finish up and talk about passive absorption, ocean alkalinity, but let me ask any questions on direct air capture. Yeah, I can't answer that because I didn't. Okay. The fans weren't running the day I was there. Yeah, but you would estimate. But it would be. Yeah, I don't know how loud it is, but that's probably a consideration. Yeah, it may not be that loud. You're not. It's not like a jet engine. You're only going a few meters per second. So but you don't want to live next door to it. So, I don't think it's a problem in Iceland because no one's near it, but that can be a consideration. That's a good question. I'll have to ask about that. Anything else? So basically, all of these things work on alkali. Now, if we look at the strong base method, where you have the basically a calcium oxide, you start with limestone, calcium carbonate, and you calcine it to make calcium oxide. What carbon engineering is doing is using that as a sorbent, and they're recycling it around in these big absorbers. Well, some people say, well, those absorbers are really, really expensive. Why don't we try passive absorption? This is take it. It's not quite throwing it on the ground and just let it react. I mean, if you do take it and put it on the ground, it will react over time. So what they want to do, these ideas of passive absorption, the company that's probably the most, or that sort of originated this, and once again probably has $1 billion of funding, is a company called Heirloom. And they talk about putting it in trays. So think of a cafeteria thing with those things where you put your trays in, have the trays with it. I actually did a little due diligence, not for Heirloom, but for another company with passive absorption, and their design did not work. Basically, you have to get enough air, in those trays, and so a lot of it's kinetics, but if you space them too closely together, your airflow going through there is going to be way too fast, and you're not going to make it. So then the question is, what type of area do you need to spread this off with? And then if you're doing that, how do you distribute it and collect it? And if it's truly passive absorption, sometimes the air is just not moving. And so you're having all this stuff just sitting there, And then if the air is really moving, you have a very windy day, if it's calcium oxide they're using, which heirloom is, it's going to blow all over the place. It's like flour. So the more I thought about it is, I just don't think passive absorption is a realistic approach. But of those 30 companies I talked about, at least 10 and maybe more are trying a passive absorption approach. So we'll see what happens there. Maybe they're smarter than me in figuring it out. But the reason people use absorbers is for a reason. It gives you good contacting. It makes efficient use of your sorbent. And I don't know if you can do it otherwise. So, but it is a problem. You know, those absorbers are expensive. They're big. And what instead of this passive absorption, what about we just take the alkali and put it in the ocean? And that's really the thought beyond ocean liming. Now, there's other things you can put in the ocean, but I think the most interesting is doing the calcium oxide. Now, why is this interesting? Well, if we put the calcium oxide out in air, at most, a molecule of calcium oxide will get 1 molecule of CO2 to make calcium carbonate. And in a lot of the passive absorption things, they're saying, I'm going to do 85%. Not only that, when you do passive absorption, it doesn't get good reaction rate unless you have a certain amount of moisture there. So it's fairly complicated. But if you put it in the ocean, it goes into the ocean carbon cycle, and basically it will end up, calcium oxide will end up as bicarbonate, because most of the carbon in the ocean is a bicarbonate. Basically, 85% will end up as bicarbonate. So for every molecule of calcium oxide, you can get 1.7 molecules of CO2 from the air. That already cuts your cost, not quite in half, but almost. Another thing that this does is it counteracts ocean acidification. So you're putting a base in the ocean is raising the pH, where the CO2 going in the ocean from the atmosphere lowers the pH. So these are both very, I think, strong reasons to consider this. There was a very good paper, if you're interested, that has a good review on this. And they say there's still many unanswered technical, environmental, social, and ethical questions. So it's not a slam dunk. The real big thing it does is it raises ocean alkalinity. But there's so much alkaline in the ocean to really do this on a big scale. It only raises the alkalinity a few percent. Will that be serious or not? Now, why is ocean alkalinity important? Well, the shellfish, I mean, that's what all shellfish are based on. They use the alkalinity to create shells. Will that harm them or not? I think initially the thinking is it's probably not going to be a serious concern, but you still have to really answer the question. I think the bigger issue of this is governance. You know, getting permission to do this, people really believing it's going to pick up the CO2, because I can't measure the CO2 going in the ocean, but we know the ocean chemistry, and we can be pretty sure it's going to happen. This borders, instead of carbon dioxide removal, sort of borders on a geoengineering, a little like the solar radiance management, and it scares people. But people are starting to consider other geoengineering options, and I think of the geoengineering options, this is probably one of the safer ones and probably one of the more effective ones. So I find it interesting. I am too old to pursue it, but I like to follow it, and there are people doing it. I know there's a professor at Caltech that has formed a company to do this. This Renforth group's out of Europe. So there are people looking at it seriously. So I think it's an interesting thing as we move forward in carbon dioxide removal. I wrote a chapter on direct air capture or this book, and this book here actually has lots of chapters on all of the different methods I discussed today. So if you want a nice reference, you can buy the book. I don't know how much it costs, maybe a couple $100, but if you just want to see my chapter, send me an email, and I'll be happy to email you back a copy of it. And time for break, okay? And we'll come back. I think we'll start the next session. I'll go back to the biofuels, and then we'll do the final thing on policy.